remember where we were? We said that this equation was exact. The only thing we did was to split u into uh plus u tilde, and to take the test function first in the finite element space and then in the complement. That was exact. This is 0 exactly, so no approximation here. And then we do, that's the problem that we have to solve for the subscales, and then we do 2 additional approximations. That's the first, no, not additional, that is in fact the first approximation. So first we define somehow this space for the subgrid scales, and then we take the subgrid scales equal to 0 on the element boundaries. That's the first approximation. In fact, that can be relaxed, as I said before. Okay, so once we do that, what do we have? Well, the first thing is that if the subscale is 0 on the element boundaries, this term is 0. So that term is 0. Okay, that term is 0. And second, we have that the problem for the subscales is precisely L of u tilde equals F minus L of UH, because we said that the space of subscales is such that this holds precisely. So this is the final method. No, not the final. This is the method that we have with these 2 approximations. Okay, that can be changed. We will see a way to change it, in particular in the applications, not in the main theory, but in the applications we will see a method to modify this assumption. And then there are methods to relax this, although we will not see them. Okay, this is very important. This is very important because now what we have is that within each element we have to solve this problem. Okay, within each element with boundary conditions u tilde equal to 0 on the boundary, and then once we solve this problem, which of course will depend on UH, so the solution u tilde will be a function of UH, then we can plug it in the first equation and end up with the problem posed in terms of UH alone. You know, that's the key point. That's it. That's the whole story. So in essence, what we do is, if we have a mesh, we have to approximate somehow the problem within each element. So for example, we have to approximate the problem here, the problem for the subscript scales. So we have to solve L of u tilde equals F minus L of UH on that domain. Obtain u tilde as a function, as a function of UH, and then put it in the first term, which is the integral over the element domains of u tilde times the adjoint applied to the test function. That's it. That's the method. Okay, and so far the only approximation has been, remember, to take that u tilde equal to 0 on the boundary, which of course is not exact. Yes, because the differential operator may have second order terms. In fact, we are interested in second order problems. And remember from the very beginning, we cannot define that integral, neither that one nor with the original operator. We cannot define this integral globally. Okay, we cannot define it globally because second derivatives. So the first derivative of a continuous function is in general discontinuous. The second derivative behaves as a Dirac delta function, and it's not square integrable. Okay, but let me stress that this is exact. Okay, why is this exact? Let me do it for scalar equations. I mean, I haven't done any approximation here. Let me do it for a scalar equation. Remember, we had the integral over omega of gradient of u tilde, for example, for the viscous term, VH. That's the type of term that we have to deal with, okay? For the convection-diffusion equation with K, whatever. The only thing I've done doing that is I have written that as the sum for all the elements. Let me write them as K. Integral over the elements of gradient of u tilde dot gradient of VH. This is exact, okay? Because the integral is additive. Now what I do, within each element, the second derivatives are well defined. So then I write it as the sum for all the elements of the integral within each element of u tilde minus u tilde Laplacian of VH plus the integral over the boundary of the element of U tilde dVH dN. That's what I've done, nothing else. And this is exact. Okay? No trick here. Why is it well defined? Because within each element, the Laplacian is well defined. And then I have a boundary term that I have to take into account. But since I will assume that U tilde is equal to 0 on the boundary, that term doesn't show up. You understand? So this is exact. No approximation. Here, the approximation is to assume that the subgrid scale is a bubble function. Why? It's an assumption. It's even better than take it equal to 0 everywhere, right? So I will comment on that later. I will comment on this. In fact, I have my own justification of that, but for the moment, let's assume that it is 0. It's just a first approximation. So remember that Galerkin is taking it equal to 0 everywhere. So now we are taking it 0 on the element boundary, but in principle different from 0. Okay, so this is the method. Okay? So we have to solve this problem within each domain. Within each domain, we have to solve this problem. And then we obtain U tilde, plug it here, and have a problem for UH alone. Of course, this is still not feasible because we don't have to solve the problem on the whole domain, but we have to solve a problem as difficult as the original one within each element. So that's still not feasible, not computably acceptable. So what do we do? Now here comes where, that point has to be answered. How do we solve for U tilde? So now we have to devise different methods, give different approximations to U tilde, a solution of that system. And the key idea is we don't need let's say, an accurate representation of U tilde. We only need the effect of U tilde on UH, because the solution is going to be UH, not U tilde. Okay? The solution is going to be UH. U tilde is something that we don't see. We only want to compute the effect of U tilde on UH. Okay? First method. The first method that was proposed, that method was proposed in the mid-90s. In fact, there is a paper in 95 by Tom Hughes who proposed that idea. This is a framework. There are things that I do in a different way, but that is a framework because you have to choose the space of subscales, you have to choose the boundary values of the subscales, and you have to choose how to solve for the subscale. So it's a framework rather than a method. So how do you solve for the subgrid scales? Let's see three different alternatives. The first one is to approximate the Green's function of the problem. So how do you approximate that? We have to solve this problem. And since U is equal to 0 on the boundary, if the Green function were known, the Green function of the problem were known, of the differential operator were known, we could represent the unknown in terms of the Green function in this way. So this is the right-hand side. We convolute the right-hand side with the Green function. That's the obtain the closed form representation of the solution. Now the idea is, of course, this is very nice, but we don't know the Green function. Of course, if we knew that Green function, we could manage to work on general domains, even if it is the Green function for homogeneous boundary conditions. Okay, so now the first point is, let's consider this approximation of the Green function, which is equal to a certain parameter that depends on position multiplied by the Dirac delta function of a point. So this is a mass representation of the Green's function. This is used sometimes. What happens if you just accept it, okay, for a moment? What happens if you use this representation? What happens is that the approximation to the solution is obtained by replacing G by that approximation, and since this is a Dirac delta function, this is only different from 0 when x is equal to y. So this is the value of the integrand, that function that we integrate, at y equal to x. Okay, so that's what we get. Tau x goes out of the integral because it's an integral with respect to y, and then that function is evaluated at x as well. Okay? So what is the conclusion? The conclusion is that u tilde is directly proportional to the residual. That's the conclusion. With the proportionality constant being, not constant, but function, the proportionality constant being tau. So how do we determine tau? For example, in the original paper, that is more or less historical, okay? So take it as just information. For example, in that original paper, it was proposed that tau has the correct mean, okay? In particular, the mean of tau, the mean of the approximated green function coincides with the mean of the exact green function. And then you get some expressions in some particular problems that are interesting, okay? Well, you see, that's a good point. That's a good point. At the end, you can understand that as a Petrov-Galerkin method, but the starting point is not that one. The starting point is the original variational equation. In a sense, we will see that, yes, you could understand that as a Petrov-Galerkin method in the sense that we will see in a minute. Okay, so that's, you approximate tau by imposing that the mean of the exact Green's function is equal to the mean of the approximated Green function. And with that, you obtain a nice expression of tau. But the important thing is that one. The important thing is that once you know that u tilde is tau times the residual, you put it in this equation and you're done. You see? Once you know that u tilde is tau times the residual, you put it here and you're done. And that's what you get. So that is tau times the residual. Look, this is minus the residual. You see? This is minus the residual. That's why I have put a minus sign here, because this is minus the residual. So this is minus u tilde. You see, all this is minus u tilde, and then you have L adjoint applied to the test function, which is what I have here. Well, in fact, in the other equation, I have transposed both terms. So u tilde times L adjoint is of course equal to L adjoint transpose times u tilde. Okay, so it's the same thing. So do you see that that is the term that we finally get? Do you all see? Because that is everything. Everything is this. All is that. Okay, so at the end, everything reduces to an expression of this form. So please let me know if you understand this, because that's the key point. Okay? So in a sense, it can be understood as a Petrov-Galerkin method, yes, because we are taking as test function VH plus minus the adjoint applied to the test function times tau. That's the test function, in a sense. Okay, so we are weighting the whole equation. We are weighting the whole equation by this term. Okay, so let me summarize, in a sense. Let me summarize what we have obtained, which is all are similar methods but not equal. So the stabilization terms we have seen are the following. Let me write it as the sum over the element, integral within each element, of a certain operator applied to the residual. And that operator, let me call it P of PH. Excuse me, a certain operator applied to the test function, sorry. We have seen three methods. In the first method, that operator applied to the test function is equal to the convective part of VH, of L. Okay? That's what we have seen in the case of SUPG method. That is SUPG. For the convection-diffusion equation, is just A gradient of B. Okay? For the GLS method, what is the operator that we have put here for the GLS method? Who reminds us? Who recalls this? In the case of the GLS method, what have we seen? What is the operator? What? L, exactly, L, the whole thing. In one case, only the convective part. In the GLS method, everything. And what do we see now that we put in that method? In this method, we put minus the adjoint of L. That method, I will call it variational multiscale. It is not called variational multiscale here, but this is what is called variational multiscale. Why? Because essentially we have split the solution into two scales. In fact, it's a two-scale method, but it's called multi-scale. You know, I mean, everything that has more than one scale is multi-scale. Okay, so that's what we see. For example, in the case of the convection-diffusion equation, the convective operator of BH is equal to A gradient of BH. The whole operator applied to BH, this is for convection diffusion, is equal to minus K Laplacian of BH plus A gradient of BH plus SVH. And minus the adjoint, let's take a look at that. Let's take a look at minus the adjoint. We have the expression for the adjoint somewhere. Where is it? Where is the expression for the adjoint? Here. It's here in the bottom. Okay. This is you see. Let's consider the scalar case. Look, the expression for the adjoint, the convective term changes sign. The diffusive term keeps sign, and then the reactive term keeps sign but has a transpose. So the minus the adjoint is K Laplacian of BH with a plus, because here we have a minus, therefore minus the adjoint has a plus, changes sign, plus, because the convective term changes sign, if we put a minus in front, is plus A gradient of VH and minus SVH. You see? These are the differences between the three methods. This is SUPG, this is GLS, and this is variational multiscale, a particular variational multiscale. You see, in all cases, the key point, the key term is the same, which is A gradient of B multiplied by the convective term in the residual, which is A gradient of U. So A gradient of B appears everywhere. That is necessary. That is what introduces streamline diffusion. Remember that. So the interpretation is important here. Okay. So all three methods share that term, and they have differences. For example, look at that. This term has a different sign here, and that has a different sign. This is not crucial. You can work with that in the analysis. It's not difficult. What is really important is to have, in all cases, A gradient of B, A gradient of U. Okay. Good. So that's the method. That's the method. We can write that method. We can write this method as a variational problem, discrete variational problem, as explained, as written here, where we modify the original bilinear form to that bilinear form, and the right-hand side to that right-hand side. Which is the modification? The modification is, so we have the original Galerkin term plus the minus the adjoint applied to the test function transpose times tau times L of U. And in the right-hand side, we have minus the adjoint applied to the test function transpose times tau times F. Okay, so that's the modification of the right-hand side. Here you see that the subscript I've used to identify the method is AGSG. SGS stands for subgrid scales, and that is an algebraic approximation to the subgrid scales, because in fact, this is very important to keep in mind. What we have done essentially in this method is to replace, remember that we are aiming at solving this equation. That is the equation that we are aiming to solve, okay? We have replaced the differential operator L by a matrix, tau minus 1, or a scalar in the scalar case, tau minus 1, so that at the end U tilde is tau times F minus U L of UH, okay? So this is the key. So we have replaced the differential operator L by a scalar, tau minus 1. So we have replaced a differential operator by an algebraic operator, okay? A matrix in the case of systems, a scalar in the case of scalar equations. Okay, that's essentially what we have done. In fact, we could have done things a little bit more complicated, and we could have designed methods that are not the algebraic subgrid scale, but this is the most popular, the most common, okay? The algebraic subgrid scale method. Is there any question up to this point? Okay, if you have understood that, that's the whole story. Then now I will apply it to I will talk about the Stokes problem, about the peculiarities of the Stokes problem, the Navier-Stokes equations, then all the problems. But in all cases, that is the stabilization term, or similar to this, and the stabilization mechanism has to be seen for each problem. For example, for the convection-diffusion equation is this term A gradient of B, A gradient of U. For the Stokes problem is gradient of Q, gradient of P, and so on. Well, that's exactly, since for linear elements, only for linear elements, it's exactly the same, because for linear elements that vanishes and we have the same thing. Yeah, for linear elements is the same. For nonlinear, for elements of a higher degree, it's not the analogy is not one-to-one. There are additional terms here and different terms in the bubble stabilization. You know, there are some differences. By the way, it is important to understand that even though here we have an expression for U tilde, you don't have to understand that expression for U tilde as an accurate one. This is not an accurate representation of U tilde. What is intended to be accurate is that integral. That integral is intended to be an accurate representation of this integral. Remember that this is the term. In fact, this is the term that we are adding. Okay, so this is the term that we are adding that the Galerkin method misses. So that number, because this is a number, that number has to be well approximated. Oh, sorry. Well approximated by this one, okay? That number has to be well approximated by this one. But you do not have to see the element, the subgrid scale as pointwise given by this value, okay? In other words, by the way, let me insist on that. Let me insist on that because this is, I think, important. You know that we have started from the assumption that the subgrid scales vanishes on the element boundaries, right? So let me plot what happens in 1D and for the convection diffusion equation with constant coefficients. Suppose that we have constant coefficients. So suppose that we have constant coefficients even in 1D. So we have said that U tilde is equal to tau times F minus L of UH. And this is equal to tau times F plus K Laplacian of UH minus A gradient of UH minus SUH. Okay, so within each element, how does this U tilde look like? Look, this is 0 for linear elements. For linear elements, P1 elements, this is 0. Nothing. What is that? This is a constant. The gradient of a linear function is a constant. It's just a constant. And this is a linear function. This is again a linear function. So essentially, and that is suppose that F is, I don't know, linear if you want. So essentially, U tilde is something that is like that. You know, discontinuous, because we will have something that will be discontinuous across elements, but it's something like that. And that tries to represent, that's the approximation that we have to U tilde. That tries to represent the good U tilde and the exact U tilde. And the exact U tilde, we have assumed that it is 0 on the boundaries, and of course will be something that cannot be captured by the finite element mesh. So it will be something like that, you know. So something complicated. That will be, in yellow we have the exact U tilde, and that's the approximation that we have. When we have moved from the equation L of U tilde equal the residual, equal to minus the residual, from here to here, we have removed all those variations, and we have just left one, let's say, piecewise linear, in this case, function. In the case in which we don't have reaction and we don't have force, it's just a constant, you see? I mean, if that term is 0 and that term is 0, it's just a constant. So we put a constant per element, you see? We put a constant per element, okay? Because we are not interested in the exact value of the subgrid scales, let me insist on that, but only on the effect of these subgrid scales on the finite element solution. Is that clear? So in fact, Now that answers the question that the method, in fact, I mean, is not a bubble function method, but the subgrid scales can be also represented by bubbles, okay? And that's what we will see now. That's residual free bubbles, okay. So have you got the idea? This is very important, okay? The method is this one, that is the method, and the first way to approximate the subgrid scales is that Green's representation, Green's approximation to the Green's function, that approximation to the Green's function. Of course, that method is not, let's say, practical in the sense that the Green function is not known. So again, we have, in the case of, for example, once we have that method, in the case for the convection-diffusion equation, which is the tau that we will use? We will use the tau that we already know that works, okay? So you can justify that this is a certain approximation to the problem's Green's function, but in fact we will use the tau that we know works, okay? And the same for the Stokes problem and so on. So there is another way to obtain the approximation to U tilde, which is by using what is called residual free bubbles that I will explain in a minute. I don't know why, well, yes, I know why. There are some letters typed in boldface characters that should be in plain italic characters because they are all scalars. So forget about the boldface here, okay? So let's consider the scalar case to explain how to introduce the residual free bubbles. Okay, so we have to solve this problem, LU tilde equals F minus L of UH, with boundary conditions U tilde equal to 0 on the boundary, okay? And now we have to approximate that. And what is the idea of using residual free bubbles? The idea is to approximate that using finite elements again, with functions that will vanish on the element boundaries, and therefore with functions that are bubbles, okay? The shape of those functions is a bubble. So we can write the weak form of the problem, and the weak form is written here. The weak form is the bilinear form of the problem applied to U tilde and tested against V tilde equal to the right-hand side tested with V tilde minus the bilinear form applied to UH V tilde. Okay, if you move that to the left-hand side, it is obvious that that is the problem that we have. Okay, and now we consider, as I said, that this space, the space of functions H1 that vanish on the boundary of each element, that is posed for each element, is spanned by a certain set of shape functions that I call here bubble functions from 1 to the number of bubbles and bub. Okay. The good thing is that we don't need many bubbles. You will see why we don't need. You could think. Remember that I said that we have to approximate now the problem within each element. You could think that now within each element we need many functions, like like a fine mesh within each element. That would be a normal, a straightforward idea. Okay, to discretize, so to speak, each domain and try to approximate the solution within each domain. However, we don't need to do that because there is an observation that simplifies things. Okay, so we approximate the problem with that basis, with this basis. So we approximate the solution. Now you see there is an approximation of the subscale by a finite element subscale. So it's different. The concept is different to what we did before. Before we just approximated the Green's function. Now we have to approximate using finite elements the subgrid scales. So we approximate those subgrid scales in terms of the bubbles. Okay, and now the problem becomes this one. So we approximate those subscales in terms of the bubbles. So we insert that in the bilinear form of the problem, and then we test with the test function that is bubble function j, and j goes from 1 to the number of bubbles that we have. So this is the standard finite element method, exactly what you have, and the only thing is that the notation I've used for the test functions is B because they are bubble-like. That's it, nothing else. Okay, perfect. Then that will give us a matrix. That will give us a matrix, and from that, inverting that system, we will be able to find the coefficients of the bubble functions. And once we obtain those coefficients will be given by what? Will be given by the right-hand side, which is given here, the right-hand side, multiplied by the inverse of the components of this matrix. Okay, that will be the expression of the coefficients of the bubble functions. And now the bubble function, exactly the solution to the problem. The solution to the problem will be the sum of the bases bi times those coefficients. So you insert the expression of those coefficients in this expansion and you get that. In fact, what I've done is I moved the integral outside because the integral is with respect to y. The integral is with respect to y, and that function, of course, depends on x. You see? I mean, I have to change the variable of integration to avoid confusion. Okay? So what you get at the end is this. Please take a look and let me know if you understand that. So here, imagine this is the integration variable is y. So we have ui equal to aij minus 1, because it goes multiplying to the right-hand side, times this coefficient, and then you put it here, and you get that expression. Okay? Good. Now, this is very illustrative. This expression is very illustrative. If you compare this expression, that's what you get using bubble functions. That's the approximation to the degree scales. If you compare this approximation to this one, what do you observe? What do you observe? You compare this, that is in the general vector case, against this, and you observe, in fact, that we have approximated the problem's Green's function by this. Okay? So, in fact, we have a certain approximation for the problem's Green's function. So, there is a clear link between this method, I mean, this approximation of the Green's, well, not this one, that one, that is the exact approximation. There is a clear link between that exact approximation and that one using bubble functions, which, let's say, can be understood as a certain approximation of g, function g. Is that clear? Good. So that's just a fact, that link. So we have a certain approximation of the problem's Green's function. There is a method, there is a particular case of that residual bubble approximation. That's what I was mentioning before. That is what is called residual free bubbles. What are residual free bubbles? So we have to solve this problem. That's the problem that we have to solve. Okay? That's the problem that we have to solve. When we approximate it, UH is the sum of the bubble functions times the nodal values of the bubble functions of the bubble degrees of freedom. Okay, that's what it is. And L is a linear operator, so that equation can be written once approximated. So that should be taken with care. This is once we approximate that. If you want, you could put an H here. That would be more precise. This is what we are doing. And UH within each element is the sum from j equal 1 to the number of nodes of the element of the shape functions of each node times the nodal value of each node. Okay? So, for example, for a triangle, we would have 1, 2, 3 nodes in the case of linear elements. Okay? N naught is the number of nodes of the element we are considering. Okay? Because that's the expansion of UH. Okay. So now that we see that this is the problem that we have to solve, we can figure out which is the number of bubbles that we really need. In fact, the number of bubbles needs to be only the number of nodes plus 1. So that means that to make it exact, if we want to compute that exactly, we will not do it because we will have to solve problems that are difficult to solve. But look, so imagine we have a triangle. We are solving the problem in a triangle. We have the number of nodes in that case is equal to 3. Okay? The number of nodes is equal to 3. And we have to solve the problem L of UH tilde, I have written an H here, equals F minus L of UH. And that this is equal to F minus the sum from J, let me say 3, to emphasize that this is the number of nodes, of L applied to the shape functions, I use a subscript here, times the nodal value at each node. Okay? And on the other hand, this is going to be equal to the sum from I equal 1 to the number of bubbles of L applied to the bubble times the nodal degree of freedom of the bubble. And I say we only need, the number of bubbles that we need is the number of nodes plus 1. In that case, it would be 4. So I'm claiming that we only need 4 bubbles. So we need 4 bubbles here. Okay. So what I'm plotting, for example, a bubble would be a function that takes the value 1 here, the value 0 at these 3 points, and 0 on the edges, of course, of the element. That would be a bubble. So it's not an easy bubble, you see. It's not that nice bubble that we saw before. So it's a bubble that takes the value 1 here, 0 at these 3 points, and 0 on the edges. So it's not that easy to construct that bubble, but it's feasible. Okay. Why am I claiming that that's the number of bubbles that we need? Only the number of nodes plus 1. Look, we define the bubbles, those 4 bubbles in our case, those 4 bubbles, such that L of the bubble Bi is equal to minus L of the shape function Ni from I equal 1 to the number of nodes. So for the first 3 bubbles, we solve this equation. And then for the last bubble, the 4th bubble, we solve the equation L of the last bubble equal to F. Okay? What happens if we do that? If we do that, it is clear that we have the solution. The solution is given by this expression. It turns out that if we manage to obtain those 4 bubbles, if we are able to compute those 4 bubbles, so the first 3 that solve this equation and the 4th bubble that solves this equation, we can immediately see that the solution, the bubble function solution, is going to be expressed by this. Why? You just have to check it. L of U tilde will be equal to L of U tilde will be equal to L of Bi, but L of Bi is minus L of Ni, and L of Ni multiplied by the nodal value of node I is precisely minus L of U plus L of B last bubble, but L of B last bubble is equal to F. Okay, so if we solve this problem, then the solution will be given by that and will be exact. You see? So if we are able to obtain those 4 bubbles, the exact solution will be this one. You understand? So this is why these bubbles are called residual free bubbles, because they make the residual to be exactly 0. Okay, so they hold exactly. Of course, again, that's not feasible. Why? Because it is not. That problem is not difficult, but not easy. And that problem, of course, to solve that independently of the force F is also complicated. Maybe to obtain the last bubble, you have to solve a finite element problem. Okay, because this is a difficult problem. So to compute that bubble, so the bubble will be this one. Okay, but to know the shape of that bubble may require to solve a finite element problem again. Okay, those are called residual field. Okay, and that is explained here. The problem is that we have to solve problems of this form. The advantage is that they don't depend on the function. Once you have the solution, you can have it forever for all functions. But this is very complicated. Those bubbles are residual free, and there were methods that were designed to change the, let's say, to simplify the calculation of those bubbles, and were called pseudo-residual free bubbles and so on. But that is not important. I have explained 2 methods to obtain the same approximation, because at the end we have something very similar. Okay, at the end. So at the end, what do we have? At the end, we want to solve L U tilde equals F minus L of UH. That's the problem that we have to solve in each domain K, or omega E. And then we have seen 2 methods. The approximation to Green's function approximation, or bubbles, or the use of bubbles. Okay, at the end, both lead to u tilde equals tau times f minus L of UH for a certain tau. Okay, both lead to the same thing. There is a third method that I haven't explained here, but it's in fact what I use, which is based on a Fourier analysis of the problem. That's in fact what I use, that I think is the simplest and definitely the one that can be applied to any problem. One can be applied to any problem. What is the idea? Let's explain that for the Convection-Diffusion Operator. And that explains, by the way, Fourier's method. I haven't the method on the slide, but that explains why you can take the subgrid scales vanishing on the boundaries. That explains why the subgrid scales can be taken to vanish on the boundary. The idea is the following. We have to solve that equation that is written here, okay? In fact, we will approximate the exact subgrid scale will be approximated by a certain approximation that I may call it like before u tilde h. Okay, that's going to be an approximation of the subgrid scale. So now the idea is that the norm, the objective is that the norm of that subgrid scale is approximately the same as the norm of the exact subgrid scale in each domain in the L2 norm. And you know that there is the so-called Plancherel Theorem that says that the norm, the L2 norm of a function, is equal to the L2 norm of the Fourier transform of that function. Okay, the Fourier transform of that function. So now is where the idea comes. We have to solve the problem L of u equals to f minus L of UH. Okay, if we Fourier transform that equation, what happens? If we Fourier transform that equation, L hat of u tilde hat has to be equal, let me call it residual, it has to be equal to RH hat. That's the Fourier transform of that. But what is the perfect situation? The perfect situation is that when you Fourier transform an operator, what do you get? When you Fourier transform a derivative, what do you get? What? A limit? An algebraic approximation. An algebraic, for example, you know that the Fourier transform of du dx in general is ik, k being the wave number, times u hat. So in general, that each derivative introduces a factor ik, I being the square root of minus 1. Okay, each factor introduces that, each derivative introduces that factor. So you have an algebraic approximation of the operator. That's what we were looking for. So that naturally gives you an algebraic approximation, and then that allows you to say that u tilde hat is equal to tau minus 1, and this, excuse me, tau, this is exact up to a certain point, times the transform of this. Okay, and then you can use Plancherel's theorem and argue that if you replace, you go back to the original space, you go back to the Cartesian coordinates, this will be an approximation to the exact one. That will be an approximation to the exact subgrid scale with more or less the same L2 norm. Physically speaking, with more or less the same energy. This is the idea. And does that work? It definitely does. Look, what happens for the convection-diffusion equation? What happens for the convection-diffusion reaction equation? What happens if L of UH is equal minus k Laplacian of u plus a gradient of u plus SU? Let's compute the Fourier transform of this. The Fourier transform of that. That is going to be, oh, sorry, because this is k is the diffusion and not the wave number. Be careful. Let me call diffusion nu here. Okay? K here is diffusion, but let me call it nu. Because the k that I said before, the little k, was the wave number. Okay? So the wave number. So this is every time I take a Laplacian, I will have the Laplacian are second derivative, so I will have the wave number squared. So that's going to be nu norm of the wave number is squared, and with a change of sign, because every time I take a derivative, I take I k, and I squared is -1, so that change will be. And then I will have minus a dot I k. Now that k is the wave number. U tilde hat. Oh, by the way, well, U tilde hat goes at the end, plus s, and that goes with U tilde. Excuse me. U tilde transpose, the Fourier transpose. You see? That's how it goes. Now, what is the point? The point is that you have to compute the norm of this complex number. And the norm of this complex number behave, the norm, because when you have to compute the L2 norm, you have to compute the modulus of this complex number. And the modulus of this complex number is what? The modulus of this complex number is nu k squared plus s squared, which is the real part, plus norm of A, norm of K, times a certain angle that I don't know between both, squared, excuse me, squared. Certain angle, let's say a cosine that I don't know. And then the square root of that. Okay? That's the modulus of this number. That's what I need to compute the L2 norm. And what about the wave number? What is the wave number characteristic in an element? The wave number within each element, all wave numbers have to behave as something of order 1 divided by the length of the element. You know that the wave number behaves as 1 over the length of the domain. Okay? So that the wave number has to behave as a certain number that I don't know divided by the length of the domain. So at the end, it turns out that that tau has to behave as I want, as is nu divided by h squared plus s squared plus a squared divided by h squared and then the square root up to constants. Which constants? That characteristic wave number that I don't know, that I can argue that appears from the mean value theorem, but that's a detail. And that constant between the two, the wave number and the velocity that I don't know. So that in fact there is a constant here, but those are constant. What matters is the asymptotic behavior. And this is exactly the same that behaves in terms of nu, in terms of h, in terms of s, and in terms of velocity, like what we said before, nu over h squared. Sorry, there is something. Oh no, sorry, that goes in the inverse of that. That tau is the inverse of that. So tau minus 1 is exactly that. Tau minus 1 behaves as this. Remember, that behaves as that. What does it mean that this behaves as this? It means that asymptotically in h, the behavior of this term is exactly the same as that. So you see, you have nu square square root, so you have something of order nu. You have a square square root, something of order a, s square square root, something of order s, and here h square square root, no, h squared to the power of 2 square root, so h squared, and the same for h here, okay? So that behaves asymptotically like the tau that I mentioned. So the Fourier analysis works in all situations, in fact, at least all the problems that we have attempted so far, and I think it's the cleanest explanation. So let me just mention, because I try not to explain my own work, but I have already mentioned that. In fact, that is the method, the idea that we favor to explain, to approximate the superior scales. Okay. Okay. End of the road. Let's see. That's it. Let's see how to apply that to those Navier-Stokes equations, the most complicated Navier-Stokes equation. Just in a minute. Okay. It's just very rapidly. We will apply that very rapidly, and we will move to the Stokes problem. So the Navier-Stokes equations in the stationary case, in the most incompressible Navier-Stokes equations, in the most complicated case, can be written in this form. So we have, for the moment, it's not very. We have a full chapter dedicated to Navier-Stokes, the convective term. Usually it is convenient to write the convective term as u gradient of u plus 1/2 of divergence of u times u. If the flow is incompressible, this is 0. So that doesn't. I will explain why this term is convenient in some cases. The viscous term minus null Laplacian of u plus the gradient of the pressure. And just for fun, I have put here the Coriolis force, omega cross u, and sort of porosity, sigma times u equals to F. So where does the Coriolis force come from? The Coriolis force comes from writing the balance equations in a system that rotates at speed omega. So it's a non-inertial frame of reference, and you know that Newton's laws are valid in an inertial frame of references, frames of reference that may move at a constant velocity, but may not rotate or have acceleration. You know, how are these systems called? The systems that move at a constant velocity without rotation or inertial frames of reference are called Galilean frames of reference. So we have inertial. If you write the system in a non-inertial frame of reference, you have to change to an inertial one and then go back to the non-inertial one. So that term appears. And also there is a modification in F due to the so-called centrifugal force, but that goes to F. And then in some cases there is a porosity in the medium that is modeled. We'll talk about Darcy's problem, so that will be clear in the case of Darcy's problem, that is modeled through a term proportional to the velocity itself. So it's a sort of friction term. Okay, so that's just written for fun, for putting everything together. It is very difficult to encounter a problem in which Coriolis forces are important and porosity is also important. So that, and here also for fun, I have modified the divergence of u equal to 0 condition by adding a certain small perturbation. Epsilon is a small number multiplying the pressure. This is called a penalty method. We will also talk about penalty methods in the case of the Stokes problem. Okay, so that's the system we wanted to solve. Okay, and that system, if you approximate that using finite elements, it has several difficulties when you use the Galerkin method. We have seen two of them. First is that is the difficulty inherited from the Stokes problem. So you see Laplacian of u gradient of p. So we have that structure, divergence of u equal to 0, and we have to use elements satisfying the superstability condition. So that's the first problem. Otherwise, we may have instabilities in the pressure. We have also seen that when we have diffusion, in that case viscosity, and convection, if diffusion is very small, we may get into troubles, and that happens. So we have to be able to deal with highly convective terms, and that requires some stabilization as well. We have not seen that, but in the case in which the Coriolis force or the permeability term are important, in fact the porosity term are important, then if viscosity is small, you also need to stabilize. We haven't seen that in detail, but that also happens. So we have a bunch of reasons why stabilization is needed. What is the idea? The idea is to apply what we have seen to that system. I will simplify it a little bit and linearize it. So the original equation, I will drop that term. That can be put but yes, I have introduced it because that could go also to the reactive term if you wish. Okay, if you assume this is given from a certain iteration, that could go to the porosity-like term. But suppose that we linearize the problem and we take the velocity u in this slot equal to a given velocity, for example, that of the previous iteration. So that's the equation that we have to solve, the first equation, and then the second equation is this one, okay, epsilon p plus divergence of u equal to 0. So the point is, this chapter is about convection-diffusion reaction equations. Why have I included the Navier-Stokes equation in this problem? In the linearized case, we can write this system as given at the beginning of the section about as this, okay, as this. So we have to identify properly which are the components of matrices matrices AI, of the diffusion matrices Kij, and of the zero-order matrix, the reactive matrix, if you want, S. And the identification is what is written here. The identification is this one. So the diffusion matrices are are all 0 except the diagonals, and the diagonals, because we have the Laplacian here, the only second derivatives we have are here, and the diagonals are given by this expression. Kii is equal to the viscosity in the velocity components and 0 in the pressure component. Okay? You see what I said before, that, for example, for the Navier-Stokes equation, the bilinear form associated, or the quadratic form associated to matrices Kij is degenerate. It has a 0 eigenvalue, that quadratic form. Okay. Okay. So those are the convective matrices. For example, convective matrix A1, delta here is the Kronecker symbol. So delta A1 has A1, A1, A1 in the diagonal. That's because of the convective term. A1, 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 A1 in the diagonal. Then it has 1 here. For I equal 1, there is a 1, 0, 0, 1, 0, 0. So that term 1 will give the first component of the gradient of the pressure, because that is multiplying the pressure, you see? That is multiplying the derivative of the pressure. So that is multiplying dp dx1. So that will give the first term. Likewise, A2 will give the second term for the gradient of the pressure, and A3 the third term of the gradient of the pressure. And that term will give the divergence of u. That term will give the divergence of u, because we have that will multiply du1 dx1, du2 dx2, du3 dx3. Okay, we have seen that before. That's the same as for the Stokes problem. Do you see that identification clearly? Okay. And finally, what about the reactive matrix, the zero-order matrix? So first, for the permeability term, we have a diagonal contribution, sigma, sigma, sigma. And since we have also this epsilon p, we have this contribution epsilon in the pressure term, so to speak, okay? And it is easy to see that the Coriolis force, when you expand the cross product, can be written as it is written here, okay? So omega 1, omega 2, and omega 3 are the components of the speed of rotation of the reference system. So what is the conclusion? The conclusion is that this system, or this equation plus this one, can be written as a convection-diffusion reaction system with the adequate identification of the matrices. Clear? Okay, so we just have to go ahead and apply directly the ideas that we have seen before. The adjoint operator has two components, the adjoint of the first equation and the adjoint of the second equation. This is the adjoint of the first equation. You can work it out very easily. The viscous term keeps sign when you take the adjoint. The convective term changes sign when you compute the adjoint. The pressure gradient changes sign. Remember that we are going to put minus the adjoint, okay? It is obvious that the Coriolis term changes sign, because when you move omega cross from the velocity to the test function, you know, the skew symmetry of the cross product makes that minus sign appear. And again, of course, the zero order term will keep sign. Is it clear? Okay. So, and the adjoint of the last equation is, it's easy to see that is this one. You can check it. The best thing you can do is you check it at home, and you will understand what the adjoint means. Okay. Perfect. Well, there is a scaling argument for the pressure that is not relevant. And now we take again the matrix tau, which we don't know, equal to this diagonal matrix, as we did for the Stokes case, and we just have to apply the general rule. That's where I wanted to arrive. The general rule is we have to add to the Galerkin method these terms: the integral within each element, or sum for all the elements of the integral within each element of minus the adjoint transpose times tau times L of UH. That's it. So the first equation is tau1 times the adjoint of the first operator, the momentum operator applied to the test function, times the momentum operator applied to the unknown, plus tau2, the adjoint, or minus the adjoint of the second component of the differential operator applied to the second component of the original differential operator. And you see here we have a change in sign. We have a gradient of v, because minus minus is a plus, so there is a minus. The convective term changes sign, but we have a minus here. The Coriolis force changes sign, but we have a minus here. The porosity term changes sign. The gradient of the pressure changes sign, but we have a minus, and that's what we get. That is what we get, plus these terms. So, what is the method to which we arrive? We arrive to a method that combines different features of what we have seen. We have seen that to stabilize convection, what is crucial? To stabilize convection, what is crucial is the term tau 1 and this one multiplied by this one. That is what stabilizes convection. Why? Because that introduces streamline diffusion. Okay? That's the mechanism to stabilize convective dominated flows. Now, this term gradient of Q, gradient of P stabilizes pressure. It's a sort of pressure Laplacian. Okay? A sort of pressure Laplacian. So that gives us pressure stability, of course, multiplied by tau. In fact, there is another important term, which is that one. Gradient, that term multiplied by that one stabilizes the Coriolis force in case in which you need it. And the other terms are all introduced for consistency reasons. So are necessary, but for consistency reasons, are not crucial. In fact, not even this one is crucial. For the Navier-Stokes equation, that one is more important. Why that one is more important? We will see that when talking about Navier-Stokes. But let me anticipate that what is written here. So how do the parameters tau 1 and tau 2 have to behave? Okay, so they have to behave as follows. That comes from either the analysis of the convection-diffusion reaction equation or from the numerical analysis. When you do the numerical analysis of the method, you see that the correct way that these parameters have to behave, it doesn't matter whether they are motivated from Green's function, from bubbles, or from Fourier's analysis. It doesn't matter. At the end, they have to behave this way. That's what the convergence analysis dictates. And by the way, that expression behaves this way. Okay? When I say behave, means that the asymptotic behavior of the parameters has to be this one. You can change the expression. You could take the square of that and then the square root, or you could take the p power of this and then the p root, or you could take, I don't know, whatever. But the asymptotic behavior has to be that one. That's what the convergence analysis imposes. So we have viscosity over h squared, the norm of the velocity over h, something proportional to the rotation velocity, and something proportional, by the way, with proportionality equal to 1 to the porosity coefficient. That's how tau 1 has to behave. And how does tau 2 tau 2 behave? It necessarily behaves as essentially as tau 1, h squared divided by tau 1. So in fact, one can show that the other parameter tau 2 has to behave as h squared divided by tau 1. Okay? So in fact, it has to behave, you can delete that one and multiply this by h squared. So in fact, it has to behave as a viscosity plus velocity times h, because h squared divided by h is h, plus the Coriolis force h squared. And in fact, you can delete that term. So that's what the convergence analysis dictates. It has to behave like that. So, you know, we said that in the case of the Stokes problem, that tau 2 term is not very important because we already had, in the Galerkin term, we had control on the gradient of u squared. You remember that? Or the gradient of u and the square of it. But that is multiplied by the viscosity. If we are interested in flows with very small viscosity, then that control is very weak. So sometimes that term tau 2, divergence of v, divergence of u, gives us additional control. Control means that we are able to bound the norm of that. That is control. What control means. So that gives us additional control on the divergence of the velocity. And you see from here that okay, yes, this is proportional to the viscosity, but also proportional to the velocity times h and to the speed of rotation times h squared. You see, that is the important term. So sometimes in which the viscosity is very small, that term can help. Okay, that term can help. That's it. That's the method. So we see that, and that's the end of the first chapter. So we have seen how to approximate systems of convection-diffusion reaction equations using that variational multiscale concept and starting from previous ideas, starting from SUPG, then moving to GLS, relating that to bubbles, and at the end explaining the final variational multiscale method. Okay, so that is for systems of convection-diffusion reaction equations in general. In particular, we have been playing with the scalar convection-diffusion equation and the Stokes problem, and then we have made a brief incursion to Navier-Stokes to see that the framework is general. Okay, so in a sense, this is, let's say, a global picture of the method, a global picture of the method. Now, we will move into particular problems. We will move first into the Stokes problem, and then we will move to Navier-Stokes. But what we will do today and tomorrow is to study in detail Stokes problem, and at the end we will see that what we have seen already, that to stabilize the Stokes problem, we can use the same technique as what we have seen. Okay, so these are the contents of this chapter. In fact, it's about the finite-element approximation in general of the Stokes problem, with many topics not touched, of course, but with other topics apart from stabilization, variational multiscale, that we will touch, because I think that they are important to understand how to approximate.
One way to choose one of these methods for computing
yes, one of these methods, what do you mean by that? Yes, those, but by the way, those methods are only motivations to arrive at this expression. But at the end, you have to choose that tau. You know, you have to choose that tau. For Green's function, you don't know what tau is because you don't know the Green function. For bubbles, you don't know what tau is because you don't know you don't want to solve the equation for the bubble. And from Fourier's analysis is what is closest to the expression of tau. But you do some approximations as well. You use Plancherel's formula, you use the mean value theorem, and so on. But at the end, you get the expression for tau. At the end, you have an expression for tau that is problem dependent. For the Navier-Stokes equation is what we have seen a minute ago. For other problems, we will see other expressions. For example, I will explain how to choose tau for Darcy's problem, or for waves, or depending on the problem that we touch, or for MHD, or so we will see expressions for tau. How are they dictated? My favorite one is this one, but you could also try to solve bubble functions in some particular cases and see which is the, again, asymptotic behavior that the parameter tau has to have in terms of the coefficients of the equation and the mesh size. Is it clear? So at the end, everything, in fact, in a sense, everything depends on how you approximate tau. Okay, the convergence analysis dictates the expression that I have written before in the case of Navier-Stokes. Okay, so let's introduce very briefly, because we have less than 20 minutes, the Stokes problem. So here, the first 4 points are not about stabilization, but about the approximation of the Stokes problem in general. So first, I will present the problem, then the basic theory for the problem. We already know it, so we can go fast in some of the points. Some have already been touched, so some are repeated. Then we will talk in more detail about mixed approximations. This is something that we escaped when we were just mentioning the Stokes problem as a convection-diffusion system. Then we will talk about the associated optimization problem and talk about penalty methods. And finally, that will be very easy because we have all the background already. We will see how to use stabilized formulations for the Stokes problem. Okay.
You can also comment on the estimates for these methods. How
yeah, I was planning to do that. I was planning to do that, but by the way, yeah, I was planning to do that. Yeah, but later. Yeah. Yes. Okay. The estimates have to be obtained, in general, are problem dependent. I was planning to give a general overview of how to obtain those estimates, and in some particular cases to show how these estimates work. Okay. So let's start. Introduction and problem statement. This is very easy for us, and we will do that very rapidly. So what is the problem? Because we have done it already, so that's why it's so easy. So the Stokes problem is this boundary value problem. We want to find the velocity. In fluid mechanics is a velocity, in solid mechanics is a displacement, and a pressure such that these equations hold with the simplest boundary condition, u equal to 0 on the boundary. Okay, so minus mu Laplacian of u plus gradient of p equal to f, divergence of u equal to 0. Okay, perfect. So these are the spaces. We already know that these are the spaces. H1 for the velocity, vanishing on the boundary for all the components. Now d, that d is the number of space dimensions. I changed a little bit the notation. Q, the space for the pressure, is L2 modulo constants. I explained that yesterday. I used the parentheses for the inner product in Q, so in L2, and that angle parenthesis to denote the duality pairing. That means nothing but the integral. It's the integral. I explained that, for example, if v is an h1 function, f can be in that space that is called the dual of h1, which is h minus 1. Okay, and that is only the integral. So the weak form of the problem is this one. We want to find the velocity in the velocity space and a pressure in the pressure space such that those two variational equations hold for all test functions v and all test functions q in the velocity and the pressure space respectively. Easy. Notation. Notation. We define the viscous bilinear form as this expression, nu gradient of u gradient of v, and it's a form that goes from v times v to the real number. It's a form, so it's this term. We call b, this is very standard, b, the bilinear form b, q times divergence of velocity, which goes from the pressure space times the velocity space to a set of real numbers. And L, the linear form L, that goes from the velocity space to a set of real numbers, which is nothing but the right-hand side of the forcing term. Okay? So the problem can be written as it is indicated here. A of ub minus b of pv equal L of b, and b of qu equal to 0. Note that the problem is not symmetric. I mentioned that yesterday, but can be easily symmetrized by just putting a minus here. If we put a minus here, it's a symmetric problem. Okay? The equations are symmetric. And of course, you see also that the bilinear form that appears here is the same as in the continuity equation, just by replacing the pressure by the pressure test function and the velocity test function by the velocity. That's what we saw yesterday, no problem. I also said that it is very important to write, or for development, to write the problem as a single variational equation. So I define capital B as a bilinear form defined on the product space times the product space, velocity pressure, to the set of real numbers. So the unknown is the velocity and the pressure, and the test functions are the velocity and pressure test functions. I define that by linear form. That linear form that only has, in fact, the contribution from the forcing term, and then those equations can be written as a single variational equation with an unknown that has two components, velocity and pressure. Why? That's what I said yesterday and today. Because if I take q equal to 0, I recover the first equation, and if I take v equal to 0, I recover the second equation. Is that clear to everybody? Okay, that is important. Good. In the Stokes problem, there is another way of writing the problem, that has theoretical and practical implications, above all nowadays. That is, to work directly on the so-called space of divergence-free functions, also called solenoidal functions. Okay, so what is the idea? The idea is, okay, that's the problem that we want to solve. Look at that problem, but we could do the following. Instead of working on the whole space V, capital V, we could work directly on the subspace of functions that have zero divergence. So from the very beginning, we choose functions that are divergence free. Okay, and take test functions that are divergence free as well. Okay, so what will happen? That equation will be automatically satisfied, and that term will disappear. Okay, so the idea is we have the problem the problem posed in space V. Okay? And in fact, we use space Q, the pressure space, to impose the divergence equal to 0 restriction. But we could choose to work directly on a subspace of V, which is J, which is the space of functions in V that are divergence free. Okay? We can work in J. If we work in J, then the problem reads as follows. Find U belonging to J such that this is true for all test functions in J. And that's the bilinear form of the problem. Nothing else. There is no mixed problem, because we are already seeking the solution in J. Okay? And that problem, you know that this is the standard, this is the same expression, for example, as Poisson's problem, but working directly in the space of divergence-free functions, right? And that problem can be understood as a minimization problem, as an optimization problem. Which is the problem that we want to optimize? It's this one. So solving this problem, A u v equals L of v, is equivalent to optimize, to minimize, in fact, that functional f defined on J, from J to R, defined as 1/2 of gradient of the norm of gradient of v squared minus fb. Or if you want, 1/2 of A of uv minus, excuse me, this is v, sorry about that, that should be v, vv, okay, minus L of v. That's what it says here. If U belongs to J is the solution of the Stokes problem, then U is the argument that minimizes functional f in the space J. Do you know that property, or do you want me to check it? Well, in fact, it's checked here. This is immediately checked. Why? So this is a functional, a quadratic functional, by the way. This is a quadratic function because here we have a quadratic dependency. How do we check that the optimal point, that in fact is a minimum, how do we check that the minimum of f is the solution to this problem? How do we check that? Well, we have to take fix u, and take an arbitrary function which is of the form u plus epsilon, another arbitrary function. Okay? So, what do we have to do to check that u is the optimal, the minimum? We have to check that that function, which now is a function of epsilon, has derivative 0 at epsilon equal to 0. You understand what I mean? So, look, we have A of uv equals L of v. And I'm saying that solving this problem is equivalent to optimize the functional f of b equal 1/2 of f of v of A of vv minus L of v. I'm saying that solving this problem is equivalent to minimizing this functional. Okay? How do you check that? Let's define. Okay, let me take an arbitrary function v of the form, if you want, let me take v as the solution to that problem plus epsilon w. Let me call it w to avoid confusions. Let me take the solution to my problem, the arbitrary function v as the solution to this problem plus epsilon, an arbitrary function w. Then f of b equals to f of u plus epsilon w. Be careful because I called here, instead of w, I used v again here. But f of v, which is this, is a function that I can call a function of epsilon. Once u and w are fixed, this is a function of epsilon. And I want to, and checking that f is minimum at u, is equivalent to say that phi is minimum at epsilon equal to 0. You understand that? Saying that f is minimum at u is equivalent to say that phi is minimum at epsilon equal to 0. And that means that I have to check that phi prime of epsilon is equal to 0. That would be the optimality condition. And to check that this is a minimum, the second derivative should be positive. at epsilon equal to 0. Do I understand that this is what I have to check? Well, this is immediately checked. Why? Because if you take the derivative with respect to epsilon of f, what is that going to be? Well, it's here I will have u plus epsilon v, gradient of u plus epsilon v, so I will have a square dependency on epsilon. When I take the derivative, the 2 will cancel with that 2, and I will have only gradient of u, gradient of v. So that's what it has. And then in that term, I will only have the derivative with respect to epsilon of the second argument, so that's why. Saying that this is equal to 0 is equivalent to say that u solves the first equation, that equation. Understand? Saying that the first derivative is equal to 0 is equivalent to say that u solves this equation. And what about the second derivative? The second derivative happens to be this, and we know that this is positive because in that case this is only the viscous part, which is positive, therefore it's a minimum. Okay, it's a minimum. Okay, this is important. This is important because in fact it's not important this weak form 2 but the weak form 1. Well, for weak form 1, remember that is weak form 1, this one is weak form 1. Okay, that's weak form 1. So it's the original mixed problem, whereas weak form 2 is this one. Okay, so what is the idea of weak form 2? The idea is that we have seen before that we could optimize that functional in J, and the function is given by this expression. And that is what we have seen. Okay? Well, instead of optimizing a functional in the little space J, we could do something else. We could optimize not in J, but in V, in the whole space, and impose that the solution belongs to J through a Lagrange multiplier. Okay, that's a standard optimization technique. So what does that mean? That instead of optimizing F, which is given here, instead of optimizing F, we optimize L, and L is equal to F, which has this part and this one, this is F, times a Lagrange multiplier multiplying the constraint that we want to impose, and the constraint is that the solution has to belong to J. That means that the divergence has to be equal to 0. And how do we impose this constraint? Simply by multiplying the restriction, divergence equal to 0, the divergence, by a test function Q and integrating over the domain. And therefore, we recover exactly the bilinear form B that we had for weak form 1. So this is the Lagrangian, okay? So the Lagrangian associated to the condition divergence of u equal to 0 is this one. So we have now that function is defined not on J but on V, and the condition that the solution has to be divergence free is explicitly imposed by this term. Now it turns out that the solution of weak form 1, remember weak form 1 is the mixed form, the solution of weak form 1 happens to be the optimal point of that Lagrangian, but that optimal point is neither a minimum nor a maximum. It's a saddle point. So it's maximum in Q and minimum in V. Okay, it's a saddle point. So that gives us an interesting interpretation. The interesting interpretation is that problem can be understood as the optimization of the so-called viscosity potential. The F is called, the viscous potential is called F, with the restriction that the divergence of the velocity has to be 0. And the important thing is that the pressure P now, from this perspective, is the Lagrange multiplier to enforce divergence of V equal to 0. How is this checked? Very easily. The only thing you have to check is that the first derivatives with respect to epsilon 1 and epsilon 2 of L are 0, and L being expressed in this form. If this is 0, you see that that is 0 if and only if U and P, if and only if U and P are the solution of the weak form 1. And then you have to check, I haven't done that, but you have to check that the second derivatives are, one is positive and the other is non-definite. So it is not a minimum, but a saddle point. Okay, it's minimum in terms of velocity, but maximum in terms of pressure. You will see very often, or you will hear very often, that the pressure is the Lagrange multiplier associated to the incompressibility constraint. And the explanation is this. Okay, that is the explanation. Have you understood that? Is it clear? Okay, so we have an interpretation. In optimization, there is also a technique to enforce that the solution belongs to J. And that technique of optimization theory is to penalize, a penalty method, to penalize the constraint. Okay? How do you penalize the constraint? Now, remember that we wanted to minimize, here we wanted to minimize f in J. Okay? We wanted to minimize f in J. Instead of minimizing f in J, we could minimize on the whole space V, but then impose through a penalty term that the restriction that the solution belongs to J is satisfied. So what we do is that. So we minimize f, that should be a bold character, that we minimize f, but we add the restriction penalized. Epsilon here is a small number, so 1 over 2 epsilon is a large number. So we multiply the restriction by a very large number. Have you seen these penalty methods in optimization? And have you ever seen that? No? No. Have you seen anything about optimization in function? I suppose you have seen what minimums and maximums of classical real functions, right? You know what a minimum is and a maximum is and a saddle point is. Yes, you know all that. And you know that that comes from minimizing functionals, right? Minimizing, or functions if you want, minimizing functions. And to minimize a function, you know what the Lagrange, to minimize a function with restrictions, you know that there is the technique of Lagrange multipliers. You all know that. Okay. But if you don't want to use Lagrange multipliers, there is another technique which is to penalize the constraint. And the way to penalize the constraint is to add something very large multiplying the constraint. If this is very large, the minimum will be reached when this will be very small. If not 0, very small. That is the idea of penalty methods. Is that clear? Okay. Now, if you work out the variational problem associated to this, so if you try to optimize this functional, what you get, I have written a superscript epsilon to stress that the solution depends on epsilon. What you get is this. You get the viscous form as before, the right-hand side, and this term leads to this additional term, which is 1 over epsilon times divergence of u epsilon divergence of p. Okay, that's the additional term. If now you write you integrate by parts and you write the equations that the differential equations that are obtained from this variational form, of course that term will lead to minus nu Laplacian of u, minus, and that term will lead to minus, remember that I have to move that derivative here, gradient of the divergence of u equals to f. Okay. By the way, if you know a little about, have you taken any course on variational methods from the classical point of view, from the optimization? Have you seen the catenary problem or no? Have you ever heard the concept of Euler-Lagrange equations of a functional? Oh, you have. You have then. So you have done that. You have optimized functionals. No? Okay. So if you see that the functional that we want to optimize is this one. These equations can be understood as precisely the Euler-Lagrange equations of this functional. So the differential equations that maybe you have seen that in the context of ordinary differential equations, and maybe not in partial differential equations. Okay. Okay. So another technique, a different technique is this is a sort of course on. Maybe I will stop here because this different technique leads us further, and I will explain that in more detail. But so far, we have seen that technique, that optimization technique, okay? We will continue tomorrow with that, okay? You see, the only remark I'll do before closing is that here, you see, we don't have a pressure. What do you think will be the pressure in this problem, in this equation, the associated pressure? If you compare that with the original Stokes problem, what do you think will be the pressure?
U of psi.
Exactly. 1 over epsilon divergence of U. 1 over epsilon divergence of U. That will be the associated pressure, okay? And that is what exactly happens in solid mechanics, for example. But that I will explain tomorrow. Okay, so I'll see you tomorrow morning.